So today we're going to be talking about derivatives and how they relate to the graph of the original function. This topic includes finding intervals of increasing and decreasing, intervals of concavity, the first and second derivative tests, and points of inflection. We're going to start off with finding intervals of increasing and decreasing without graphing the function, and then using these intervals to find whether a critical number is a relative maximum or relative minimum. So the first step to find the critical numbers of our function, and to do this we're going to find f prime of x. Okay, and the critical numbers of f of x are where there is a top of a hill or mountain or the bottom of a valley. So this, in terms of f prime of x, is where f prime of x is equals 0 or is undefined. So this f prime of x is never undefined, so we're just going to find where it equals 0. Factor out the 6x. And now we can say that f prime of x equals 0 when x equals 0 or negative 3. So now that we've found the critical numbers, we're going to create a number line. And to find where f of x is increasing or decreasing, we're going to test values in between these critical numbers, and we're going to plug them into f prime of x and see whether they are positive or negative. If they are positive, then f of x is increasing, and if they are negative, then f of x is decreasing. So let's plug in negative 4 over here, and then you get 24, so that's positive. Let's plug in negative 1, and then you get negative 12. You plug into f prime of x, so that would be a negative number, and then we're going to plug in 1 over here, and then you get a positive number. So we can also draw, in terms of f of x, increasing, then decreasing, then increasing again. And we can visualize the graph like this. It's going to look something like that. We have our points here, the critical numbers right there and there. And so here we can clearly see where the intervals of increasing and decreasing are. So we can write out f of x is increasing on the intervals negative infinity to negative 3 and 0 to infinity, and f of x is decreasing negative 3 to 0. And we can also talk about whether our critical numbers are relative maximums or minimums. And since this one here is increasing and then decreasing, we can say that it is a relative maximum. And since this one is decreasing and then increasing, we can say that it is a relative minimum. This method is called the first derivative test because we're using the first derivative to get our solution. Now we're going to talk about concavity and how understanding concavity can help us determine relative maximums and minimums. So first we have to understand concavity. So this is an example of concave upward, and this is an example of concave downward. So let's define concavity. So if we draw on some tangent lines, we can see that as x is increasing, going to the right, the slope of the tangent lines are increasing as well. So we can say if this function is f of x, the slopes of the tangents are represented by f prime of x. So if f prime of x is increasing, then f of x is concave upward. So we also know that if a function is increasing, then its derivative is positive. So the derivative of f prime of x is f double prime of x. So when f double prime of x is positive, our original function is concave upward. So we can do the same thing for concave downward. If we just draw some tangent lines again, we can see that f prime of x is decreasing, or f double prime of x is negative. So now we're going to define points of inflection. A point of inflection, or a POI, is the point where a function, f of x, changes concavity. So it can change concavity from concave upward to concave downward, or vice versa. And since we know that f of x changes concavity when f double prime of x changes from positive to negative or negative to positive, we can also say that a point of inflection is where f double prime of x changes signs if the function is f of x. So now let's define and see how the second derivative test works. So first let's define it. So the second derivative test says that if f prime of c, any number or any x value c, equals 0, and if f double prime of x exists on an open interval containing c, then we can say three things. One, if f double prime of the x value c is greater than 0, then there is a relative minimum at c, comma, f of c. And two, we can say that if f double prime of c is less than 0, then there is a relative maximum at c, f of c. And finally, we can say that if we find that f double prime of c is equal to 0, then no conclusion. If f double prime of c equals 0, then there is no conclusion to be drawn from the second derivative test, and you must use the first derivative test to find what you need. For example, I'm going to use the same function that we used for the first derivative test just so we can see that the second derivative test actually works. So again, our f of x equals 2x cubed plus 9x squared plus 3. Okay, so in the second derivative test, we also need to find the zeros of f prime of x. And we remember that they are at x equals 0 and x equals negative 3. So now, we still need to create a number line, but this time we're going to use the y values of f double prime of x. But we're going to plug in these numbers, the critical numbers, not numbers in between the critical numbers. We are going to plug in the critical numbers into f double prime of x. So if we plug in negative 3, well, first we have to find f double prime of x. So we can find it really quickly. Plus 18. Okay, and so now we have to plug in negative 3 into this. So if we plug in negative 3, we get negative 18. So since this is a negative number, it is concave downward. And if we plug in 0, we get positive 18. So it is concave upward. So using this, we can see once again whether these critical numbers are relative maximums or minimums. You can do this, or you can just visualize it in your head, or you could also draw out how the graph would look using this concavity information with these critical points. And then we also know that somewhere in between here, f of x changes concavity at the point of inflection. Okay, so now back to intervals of, or now back to whether these are relative maximums or relative minimums. So since it is concave downward, we know that this is a relative maximum. And since this is concave upward, we know that this is a relative minimum. Okay, now finally, finding intervals of concavity. In order to do this, we need to find when f double prime of x changes signs, which is also when f of x changes concavity. So we need to set f double prime of x equal to 0 to find when it crosses over the x-axis and changes signs. So if we solve this, we get x equals negative 3 halves. Okay, and so this, at x equals negative 3 halves, we have our point of inflection here, which is between negative 3 and 0. So we can say that the function f of x is concave downward from negative infinity to negative 3 halves, and it is concave upward from negative 3 halves to infinity.